Hello and welcome to this lecture on Bode Plots. In this lecture, I am going to tell you about what are Bode Plots and how to plot the Bode Plots for different transfer functions. To begin with, what is Bode Plot? Bode Plot is a part of the frequency response analysis for control systems. In a frequency response analysis, to tell you very briefly, if you give a input to a linear control system, let us say that you give an input like of this nature a sine omega t, which is a sinusoidal input. If the control system is a linear control system, then the output will also be sinusoidal. The output and input will be differing in terms of two quantities. One quantity is the magnitude, here it is shown as b. Another quantity is phase angle or phase difference, shown here by phi. So in short, what is frequency response? Frequency response is study of the variation of output magnitude B and variation of output phase angle phi as frequency omega varies from 0 to infinity. I'll repeat, frequency response of a linear control system is nothing but the study of the variation of the output magnitude B and the output phase angle phi as omega varies from 0 to infinity. So there are various methods of studying this relationship between the frequency and the magnitude and frequency and the phase angle. One of the ways is to use something called as Bode plots. So Bode plots are named in the honor of H.W. Bode, and it has two plots. It consists of two plots, and these plots are plotted on semi-log papers. So what are semi-log papers? Semi-log papers will have one of the axis has a linear scale and another axis has a log scale. So just now we have discussed that we have to plot the output magnitude B and output phase angle phi as frequency varies, omega varies from 0 to infinity. So to cover large ranges of omega, so if I want to plot magnitude B for say zero point 0.1 omega, I want to plot B for 1 omega equal to 1, I want to plot B for omega equal to 1000, 10,000. So to cover such large range of frequencies on a single graph, it is difficult in a linear graph. That's why what we do, we use the x-axis as a log graph so that we can cover a large range of frequencies, whereas the y-axis is our usual linear scale. So omega frequency will be plotted on the log scale and magnitude and phase angle will be plotted on the linear scale. So coming back to the Bode plots, there are two plots involved in Bode plots. One is magnitude versus omega. But in Bode plots, the magnitude is first converted into a special form known as decibels. So the unit of magnitude is decibels for Bode plot. And how do you arrive at decibels? So to arrive at decibels, you have to multiply the magnitude with 20 log to the base 10. So for example, you have a transfer function g of s. You convert that transfer function into g of j omega by replacing s by j omega. You will get this transfer function g of j omega. Take the magnitude of that transfer function and multiply that magnitude with 20 log to the base 10. Whatever value will come out is called as the magnitude in decibels. This particular magnitude quantity will be on the y-axis, and on x-axis will have frequency on log scale or omega on log scale. So this is the first plot, that is called as the log magnitude plot, wherein we have magnitude in decibels on y-axis, on x-axis we have omega on log scale. This will be more evident when we take an example. Now the second plot in Bode plot is called as a phase plot. Second plot is a phase plot. What is phase plot? It is nothing but the graph of the output phase angle phi versus omega on log scale. So as you change the value of omega from 0 to 0.1 to 1 to 10 to 1000 to infinity, what will be the changes happening in phi? So that particular graph is known as the phase plot. So when you combine these two plots, magnitude plots and phase plots, the combined plots are known as Bode plots. Now, a quick revision of a simple what do you mean by magnitude and phase angle. So, suppose you have a number, complex number represented by a plus jb, then the magnitude of this number is given by under root of a square plus b square. So, this is how you are going to calculate the magnitude of any complex number. And if you want to find out the phase angle, it is nothing but tan inverse of b by a, where b is the part, this part, which is along with j. So phi is tan inverse b by a and magnitude is under root a square plus b square. So these are the basic, this is the basic of the Bode plots. Now what we are going to say is, now we are going to actually see the steps for drawing the Bode plots. So how do you draw the Bode plots? So the first step for drawing Bode plots is, first of all, you have to write the open loop transfer function in a standard time constant form as given here. So this is the standard time constant form. So what do you mean by standard time constant form? So first of all, you replace s by j omega. So you have g of s and h of s in your control systems. You have studied this in the earlier units. So whenever you get a open loop transfer function in this form g of s, you replace this s by j omega. So we put real part as 0 and we only put s equal to j omega. Replace s by j omega. Whatever, what you will get is, you will get this function g as a function of j omega. And that should be arranged in this standard form which is shown here. Okay. So the standard form is very important. You see, first you have constant separate. Then you will write 1 plus j omega something. So like, for example, in g of s, you have a term s plus 1. So the term s plus 1, or let's say s plus 2. So the term s plus 2, instead of writing s plus 2, I will have to take 2 common and I will have to write 1 plus s by 2 or 1 plus 0.5 s. So I need everything in 1 plus form. So I'll have k 1 plus j omega ta. If you replace s by j omega, then this s will be replaced. Ta is called as the time constant. Then 1 plus j omega tb and so on. So whatever remaining terms are there, that you are going to write in the numerator. Similarly, in the denominator, you will have 1 plus j omega t1, 1 plus j omega t2. So whatever s plus terms are there, those have to be converted to 1 plus terms. Appropriately, accordingly, you will have to take the constants out of the bracket. Then there are two more terms which can be there. J omega raised to power r. This term can be there. So j omega means s power r. It can be, r can be 1, 2, 3, any value. So j omega power r means it can be, let's say, if I write s square. If I write s square, if I have a s square term in the denominator, then this will be j omega raised to power 2, where s is j omega, r is 2. If I have a s cube term in the denominator, then this will be j omega raised to power 3 and so on. So this is another term. And then there can be a complex conjugate term like this, which is your standard second order system. 1 plus j 2 zeta omega by omega n plus j omega by omega n whole square. This is nothing but your standard second order system, complex conjugate poles. So these kind of factors are possible whenever you have any kind of a transfer function, any kind of a open loop transfer function. These kinds of terms are possible, and we will draw the Bode plots for all these terms or these factors. So the second step, so first step is to bring the open loop transfer function in the standard form as we have seen. Then we will identify these factors. So first of all, the factor is, first factor is constant gain k. This factor here, this constant gain k. So this is our first factor. Then we will draw the Bode plot for poles at origin, that is 1 upon j omega raised to power r. This is the second factor, 1 by j omega raised to power r. This is nothing but poles at origin. If you draw this in s plane, then if you have s square term, there are two poles at origin. So this is your s square term, indicated as 1 upon j omega raised to power 2. Then you can have poles on real axis, that is 1 upon 1 plus j omega t1. So these terms, 1 upon 1 plus j omega t1, 1 upon 1 plus j omega t2 and so on. This is the third term. Then we may have poles on zeros on real axis. That means the numerator terms, 1 plus j omega ta, 1 plus j omega tb, all these terms. And finally, the complex conjugate poles. So you may have complex conjugate poles like this, 1 upon 1 plus j 2 zeta omega by omega n and j omega by omega n whole square. So we will have to draw the magnitude plot and phase plot for each of the terms. So for k, for 1 by j omega raised to power r, for 1 plus 1 by 1 plus j omega t1, 1 plus j omega tb, etc., and this term, etc. And then we are going to add all these plots together to get the final Bode plot. I hope that you have understood. A quick recap. What are Bode plots? Bode plots are nothing but there are two plots involved in Bode plots. One is called as magnitude plot or the log magnitude plot, in which on y-axis we have the magnitude in decibels. Decibel means 20 log to the base 10 g of j omega, and on y-axis, x-axis we have omega on log scale. Then second plot in Bode plot is phase plot, wherein on y-axis we have phase angle, on x-axis we have omega on log scale. Okay, and then first thing we do is we bring the transfer function in the standard form, and then we identify the factors. Now we will plot the log magnitude and phase plot for each of the factor, and then we'll combine them all to get the final Bode plot. So we'll see all the factors now one by one. So the first factor for us to see is the constant gain k. Constant gain k. Okay. Now, by definition, there are two plots. One is magnitude plot and another is phase plot. So what is the magnitude plot? I have to take the magnitude, multiply the magnitude by 20 log to the base 10. That means I have to take the log to the base 10 of the magnitude and then multiply it by 20. So what is my magnitude? If I have only gain k, what is the magnitude? Gain k is nothing but only magnitude is there. There is no j term. So I can write this as k plus j0. I can write this as k plus j0. So in a plus jb form, magnitude will be only k. If I find out the magnitude, it will be only k. So for getting decibels out of this k, first of all, I'll take the log of k. First of all, I'll take the log of k, but which log? Log to the base 10k. And then I will multiply this with 20. So whatever value I'll get, that is called as magnitude in decibel. Now, if you see this expression 20 log to the base 10k, there is no omega term involved in this expression. So whether omega is 0.1, whether omega is 1, whether omega is 10, 100,000, doesn't matter. Whatever may be the value of omega, even if we vary omega from 0 to infinity, magnitude will remain same, constant. So how the plot will look like then? So here you can see, if omega is changed on the log scale, even if I go on increasing omega, there is no change in this magnitude. So magnitude will remain constant. For example, if I take the value of k as 1, if I take the value of k as 1, what is the magnitude? What is I should have taken this k as 10. Suppose I take k value as 10. So what is the 20 log to the base 10? 10. If you take log to the base 10 of 10, that comes as 1. If you multiply it with 20, it comes as 20. So my magnitude will be 20 decibels. My magnitude will be 20 decibel at omega equal to 0.1. If I take omega, let's say that initial point, this point is omega equal to 0.1. This is the initial point. Even if I make omega equal to 1, still my magnitude will remain 20. If I make omega equal to 10, still my magnitude will remain 20, and so on. So whatever may be my omega value, my magnitude will remain constant. That's why I get a standard line, a simple straight line which is parallel to the x-axis. Okay. So what is the log magnitude plot for a constant gain k? The log magnitude plot for a constant gain k is a straight line which is parallel to x-axis. Okay, straight line parallel to x-axis. That is what I get. So if you get any constant k, take the log of it, log to the base 10, multiply with 20 and draw a straight line with whatever value you get. So if I take k equal to 1, I'll get 0 line. If I take k equal to 10, I'll get 20 decibel. If k value is below 1, if k value is less than 1, then I'll get a negative line. If k value is greater than 1, then I'll get a positive line. Okay. So, but still the line will remain parallel to the x-axis. So if k value is 10, I'm getting a line, this green line. Let's say k is 5. So for 5, I'll get another line which is like this. It will be lower than this line. Magnitude will be smaller. If I take a negative value, if I take k equal to 0.5, I'll get the horizontal line on the negative side. So that is all about the gain. But that is one part of the Bode plot. So we have simply plotted the magnitude plot. Now to plot the phase plot, now you see k can be written as k plus j0 or a plus jb, What is the formula for angle? We have seen tan inverse b by a. Here b is 0 and a is k. So okay, so you compare this with a plus jb. So k plus j0 is compared with a plus jb. All right. So here your k is a and b is 0. So what will be the angle? Tan inverse b by a. So b is 0, a is k. So tan inverse of 0 is 0. So what will be the angle? It will be always 0. So the phase plot will be a 0 degree line, that is line coinciding omega on log scale. So this particular line which you can see, or this x-axis is your phase plot. Whatever may be the value of omega, whatever may be the value of omega, angle will always remain as 0 degrees. So this is your 0 degree line. Okay, this is your 0 degree line. This is minus 90. I have just shown minus 90 here, minus 180 here, but your angle will not change because this is a constant term, right? So these are the two plots for first factor, that is gain k. For the first factor we have done this for the first factor, okay, constant gain k. Now actually we'll go for the second plot now, or the second factor, which is poles at origin, 1 upon j omega raised to power r. That is the second factor. So how it works? So if you look at the second factor, here, the magnitude plot can be given by 20 log to the base 10 magnitude of 1 upon j omega raised to power r. Okay. So, what will be the magnitude of 1 upon j omega raised to power r? J will go. You have to simply remove j. So, it will remain 1 upon omega raised to power r. And if I take the reciprocal, I can write omega raised to power minus r. So, simple. Okay. Remove j and take omega power r in the numerator. It will be 20 log to the base 10 omega raised to power minus r. Now, since this is a log, I can also rewrite it as minus 20 r log to the base 10 omega. Okay. Now, let us take this equation minus 20 r log to the base 10 omega and see what kind of a line we'll get if I go on changing the value of omega. Because ultimately, what is magnitude plot? Magnitude plot is nothing but plot magnitude when I change omega. So I create a simple table, and for simplicity I take the value of r as 1. Okay, so instead of writing minus 20 r log omega, I'll write minus 20 log omega. So here you can see, initially I put the value of omega as 0.1. If I substitute the value of omega as 0.1 in this equation, okay, then I'll get minus 20 r I have taken as 1, minus 20 log of 0.1, log to the base 10, 0.1. Okay, this log 10 omega, this log 10 is basically log to the base 10. Please mark this correction. This log to the base 10 of 0.1. So if you calculate that, I think that value should come as minus 20, and minus minus will become plus, so I'll get plus 20. If I put omega equal to 1 in this equation, log to the base 10 of 1 is 0. So I'll get answer as 0. If I put omega equal to 10 in this expression, if I put omega equal to 10 in this expression, log to the base 10, 10 is 1. So I'll get minus 20. So I get three values. If omega is 0.1, my magnitude is plus 20. If omega is 1, my magnitude is 0. And if omega is 10, my magnitude is 20. So my frequency is increasing 10 times. You can see here from 0.1 to 1, there is a 10 time increase. From 1 to 10, there is a 10 time increase. So for every 10 time increase, there is a change in the value of magnitude by 20. So here the value of magnitude when omega was 0.1 is 20 plus 20. Then it has reduced by 20 and it has become 0 when my frequency is increasing 10 times. So when my frequency is increasing, when my frequency is going from 0.1 to 1, when the frequency goes from 0.1 to 1, that means there is a 10 times increase in frequency. My magnitude is going from 20 to 0. Okay, 20 to 0. So this is what is happening to the magnitude. When my frequency goes from 1 to 10, there is a 10 time increase. My magnitude is going from 0 to minus 20. Okay. So what is happening? As it goes from 1 to 10, magnitude is going to minus 20. So this change is defined as a line with slope minus 20 decibel per decade. Okay, as you can observe here, this is nothing but a line with slope minus 20 decibel per decade. What is decade? Decade means when your frequency changes from 0.1 to 1. This is called as a decade. 10 times frequency is a decade. 1 to 10 is a decade. Okay, and what is decibel? Decibel is nothing but 20 log to the base 10 magnitude omega. Okay, so for every decade there is a change in the value by minus 20. So we say that it is a line of slope minus 20 decibel per decade. If I draw it on the graph paper, this is how it is going to look like. Okay, so when omega is zero point 0.1, so here I have drawn this. You can see here this magnitude in decibels is on y axis. Okay, I am drawing the magnitude plot. On y axis I have magnitude in decibel. At the origin, at this point the magnitude is 0 decibel. At this point the magnitude is 20 decibel. At this point the magnitude is 40 decibel. So this is the scale I have marked. And since this is a log scale, at the origin my frequency is zero point 0.1, then this frequency is 1, then this frequency is 10. This is the benefit of log scale, that in a small length, in a small distance, I am getting frequencies from zero point 0.1 to 10. So zero point 0.1 to 1 is 10 times, 1 to 10 is 10 times. So this is called as a decade. This is your decade. When your frequency increases by 10 times, 1 to 10, this is called as a decade. This is known as a decade. Okay. And as you travel one decade, how much magnitude change is happening here? Your magnitude is going from 20 to 0. You can see at this point your magnitude is 20, and at this point your magnitude is 0. So this is the change, 20 decibel per decade. Okay, further as you go from 1 to 10, your magnitude is now reducing to from 20 to minus 20. If I project this line here, I'll get it here. So this is what you are getting. So here as you go from 1 to 10, your magnitude has reduced from 0 to minus 20. As you came from 0.1 to 1, your magnitude has reduced from 20 to 0. As you came from 0.1 to 1, यहाँ से यहाँ तक जैसे आए आप 0.1 to 1, your magnitude has reduced from 20 to 0. As you go from 1 to 10, your magnitude has reduced from 0 to minus 20. Okay, so this is called as 20 decibel per decade. So what is the magnitude plot for poles at origin? It is written here. The magnitude plot is a straight line of slope minus 20 r decibel per decade passing through 0 decibel line at omega equal to 1. If you observe, carefully, you will find that, sorry, if you observe carefully, you will find that at this point, when omega equal to 1, your magnitude is 0. At this point, when omega equal to 1, your magnitude is 0. That's why it is said that the magnitude plot is a straight line of slope minus 20 r dB per decade passing through 0 decibel line at omega equal to 1. Now, what is R? R is the multiplicity of poles. So, the value of R can be any value. It can be like, it can be 1, it can be 2. In this case, I have shown for 1. Suppose R is 2. Suppose R is 2. That means I have a S square term in the denominator. Suppose R value is 2. So, I will have a S square term in the denominator. So, S square terms means R is 2. So, in that case, what will be my slope? Minus 20 R. So, R is 2. So, minus 40 decibel per decade. So my slope will be minus 40 decibel per decade. So that line will start from this point, minus 40 decibel. So at point 1 my magnitude will be plus 40, at 1 my magnitude will be 0, and then again it will become minus 40. Okay, so this will be my line. Okay, so this is for r equal to 2. If I make r equal to 3, then my slope will further increase. It will become 60 decibel per decade, and so on. So this is the graph of magnitude for poles at origin 1 upon j omega raised to power r. Now in real life, you will be drawing this graph on an actual semi-log paper. So for your benefit, uh, I am going to show the same thing on the semi-log paper. So same thing I have done here. Here you can see on a semi-log paper, you can select one line like this, which can be shown as 0 decibel line. This is your 0 decibel line or the x-axis. If you go above, your magnitude will increase. So I am taking this 2 centimeter as plus 20 and another 2 centimeter as plus 20. So this point is 40 decibel. This point is 20 decibel. This point is 0 decibel. Similarly, on negative side, this is minus 20 decibel, minus 40 decibel. Okay. Now, what is a decade here? You can see in the semi-log paper here, 1 is written. This 1 means the first point. So the next point, next one is written here. So this is your 10 times frequency. So if I take this point, if I indicate this first point as point 1, then 10 times frequency I'll get here. So I'll get this point as 1. Then again 2, 3, 4, 5, 6, 7, 8, 9, 10 is written here. So this means this is another 10 times frequency. So this is one decade. From this point till this point, this is one decade. From this point till this point, this is one decade. Okay. So for minus 20 decibel per decade line, how you are going to draw? So first you identify this point plus 20, then identify at omega equal to 1. At this particular frequency omega equal to 1, magnitude is 0. So this is the second point. Then third point you can have at omega equal to 10, magnitude is minus 20. So this is your third point. Join these 3 points by a straight line and you will get the magnitude plot. So this black line which is drawn is the magnitude plot for 1 upon j omega. This is the magnitude plot for 1 upon j omega. Its slope is minus 20 decibel per decade. If it is 1 upon j omega square, if it is 1 upon j omega square or s square, then I'll get this red line. And the slope of this red line is minus 40 decibel per decade, which is shown here. Okay. So in short, what is the plot for if you have a term 1 upon j omega raised to power r or 1 upon s? This is not in this is 1 upon j omega power r is nothing but 1 upon s power r. Okay, you can replace this s by j omega. So if I have a term 1 upon s, simply if I have a term 1 upon s, what will be the slope? Minus 20 decibel per decade. If I have a term 1 upon s square, the slope of line will be minus 40 decibel per decade. What is a decade? When frequency increases by 10, it is called as a decade. Okay, and it has to pass through omega equal to 1. So the magnitude will be always 0 when omega is 1. So one point you will always get at omega equal to 1, this magnitude will be 0. So it will cross the x-axis. Right. Now finally the phase plot. So phase plot for 1 upon j omega raised to power r, again you can write 1 upon j omega power r as 1 upon 0 plus j omega power r, that is 1 upon a plus jb. You assume r equal to 1. Later on you can assume higher values of r. Let's say I take r equal to 1. So phi is nothing but minus tan inverse of b by a, because this is in the denominator. So this is a plus jb in the denominator. Angle is minus tan inverse of b upon a, because for the numerator angle is 0. For this term, for this entire term, for numerator the angle is 0 minus the denominator angle. Denominator angle is tan inverse b by a. So b is omega and a is 0. So minus tan inverse of omega by 0. This will come as omega by 0 is infinity. Anything by divided by 0 is infinity. So I'll get minus tan inverse of infinity or minus 90. So my angle phi will always be minus 90 for all values of omega. So whatever may be the value of omega, my angle will remain minus 90 degrees. So the phase plot is very simple. Again, you can take a graph paper like this, or on the same graph paper in the lower portion, you can draw a x-axis for 0 degree line. Then 2 centimeters below, you can take minus 90. Further 2 centimeters below, you can take minus 180. But whatever may be the value of omega, if it is 1 upon s or 1 upon s square or 1 upon s cube, whatever may be the value of omega, uh, in this case I have taken as 1 upon s. So whatever may be the value of omega, for 1 upon s, it will always be a minus 90 degree line. It will be always a minus 90 degree line. For other values of r, you can similarly find out what will happen. Right. So in this lecture, we have discussed what are Bode plots. So very quick revision. I know too much is there in a single lecture, but you can easily make it out if you read it once again. So frequency response analysis means you give a sinusoidal input and observe the magnitude and phase of the sinusoidal output as frequency changes. So whenever you want to study frequency response, you have to remember two things. You go on changing the value of omega, that is frequency, and observe the magnitude and phase angle. For observing magnitude and phase angle, there are various graphs. One graph is called as Bode plot. If you plot magnitude versus frequency, it is called as log magnitude plot. If you plot phase angle versus frequency, it is called as phase plot. Magnitude is first converted into decibels by taking the log of the magnitude and then multiplying it with 20. Phase plot simply will take the phase angle. Then we convert these transfer function into the standard transfer function, and then we take one by one factors. In today's lecture, we have seen two factors, k and 1 upon j omega raised to power r. So for k, the magnitude plot is a simple straight line parallel to x-axis. Depending on the value of k, if k is greater than 1, then this will be positive. If k is less than 1, it will be negative. For k equal to 1, it will be a 0 line. Phase angle will be always 0 for a constant. Then we have seen 1 upon j omega raised to power r. So in this case, there will be a straight line of slope minus 20 decibel per decade if it is 1 upon s, or 1 upon j omega. If it is 1 upon j omega square, the slope will double, it will become minus 40 decibel per decade, and so on. What is a decade? Decade means when you travel for 10 times of frequency. So on a graph paper you can see this is a decade. When you go from one to another one, this is a decade. Then this is another decade. From here to here, another decade. This is another decade. And decibels is on y-axis and decade is on x-axis. I hope you have understood the both the factors k and 1 upon j omega raised to power r. In the next class we will see the remaining factors, that is poles on real axis, zeros on real axis, and the complex conjugate poles. Thank you.